Hello guys, welcome to our third or let's say second lecture on computational fluid dynamics, and today I want to explain you something about flow fields. Flow fields, the subject doesn't seem really scientific, but what I want to mention here, I want to explain you why there is a really strong connection about computational fluid dynamics and graphic visualization of fluid flow, even in numerical results or in experimental results. And these are one of our main research topics, and we try to do a lot in visualization of fluid flow. And here's some essentials about this topic. Maybe first, before we start, I want to mention again the three main steps of computational fluid dynamics. We have at first the pre-processing, the solution process, and the post-processing. And when you work on this workbench, the workflow of these tools are really good connected. The workflow is running like it is in one program, but in former time, when it was more handwork to do CFD, there was more interfaces between the different programs, and you have to copy some data from one program to another program. It was a lot of work, and there were three main steps. The pre-processing step, where you generate your mesh. That's one of the major topics of pre-processing I showed you in the last lecture. And then there comes the solution process. Solution process is maybe a step you didn't really notice if the program works, but if you have to program the CFD code on your own, it's really most scientific part of the work. You have to solve the differential equations, and I've done a lot of this. I programmed my own CFD code during PhD thesis. So there's a lot of work, but today if it works, you don't have a lot of work with solution processes. It's just time consuming. You have to wait overnight, or you have to wait some hours until your solution is finished. And then comes the most, maybe for people who are interested in arts a bit, and in pictures, and in nice computer graphics, then comes a step where you do the post-processing. Your results are here, or your measurement is here, and you have to visualize it. And that's a process also of communication. You have to show your customer, you have to show your teacher, or I have to show my students what's data about. I have to explain something about fluid flow. And fluid flow is something that is difficult to explain, because normally we as humans, we don't see the turbulence, or we don't see the fluid flow. We might see it if there's some smoke or some clouds, then we see it. But in most of the cases, we don't see the fluid flow of air. We notice it, but we don't see it. Okay, and one important, I have a sign from Eunice Schengel from his great book about fluid dynamics. Notice CFD does not mean colorful fluid dynamics. Okay, that's right. There are a lot of colorful work, a lot of computer graphics that are done during post-processing, but on the other side, somehow it has something to do with colorful fluid dynamics, because we want to explain something, and we have to explain it in a good way, in an interesting way. So maybe, it's a bit of a joke, but you will see. I think computational fluid dynamics is really interesting for students, or is interesting for many people, because of the nice graphics and the usage of the graphic cards. So, okay, let's look at the ways of post-processing now in this lecture. In this lecture, I will teach you something about flow fields, about fluid flow, and about the post-processing, how we can visualize flow. Okay, and there are some ways of post-processing. We can do it graphically, of course. We can do vector plots. I will explain you what are vectors, what is a vector. We can do contour plots, we can do isosurfaces. What is the isoline? What is the isosurface? What does this mean? Will explain you something about flow lines and streamlines, and of course animation. Animation is a strong feature to explain something. Many things, if you see them on a picture, you don't understand what's happening, but if you see some movement, some movie, it's better and easier for you to understand. Even if you are just doing a CAD or 3D model, if you only see the picture, you've never seen it turning around. It's sometimes hard to understand how the geometry look like. But if you then turn it around and play a little bit with it, you get a feeling about it. And if then afterwards you see again the same picture, the same 3D model, you understand the geometry. Okay, and of course there are also alphanumerics. Alphanumerical features we can use. We can do integration, integral values. What are integral values? Yeah, we can evaluate physical values. For example, drag, lift, torque, force. That's all data we can get from our pressure fields, from our flow fields. And we can make standard deviations. We can make average values. Yeah? Do you want to see a fluctuation, or do you want to see an average value? That's a question. Okay, we can visualize minimal and maximal values. It's different if we visualize the mean value of a flow, of a fluctuation, or the maximum or the minimal values. And we can also, a big topic in computational fluid is a comparison with experimental data. We have experimental on one side and numerics on the other side, and we must compare it. How can we do this? And there's another question, or another big thing. If you only have one CFD simulation, sometimes you don't have a feeling if this is right or wrong. And if you do a geometry or a boundary condition variation, and you have more results and you can compare them against each other, it's much more easier to find optimal geometries or optimal boundary conditions. Okay, so let's come to the topic, flow field. What is a flow field? I think everyone have seen, even if you never heard of CFD in your whole life, every one of you knows what is a flow field. And if you, because you have them everywhere in real life. For example, if you watch the news, if you watch television at night, or you look into the internet about the weather forecast for the next week or for the next day, you look at the result of computational fluid dynamic simulation. And what is a flow field? A flow field, for example, is a weather forecast. Here we have a nice map of Central Europe, and I'm a bit interested in weather forecast also, and in numerical simulation of weather. That's quite interesting topic. And so I often look at different weather maps, and for example, if we here have Europe, we have Madrid, Rome, Istanbul, Berlin, Kiev, Moscow at the top, and here's Iceland, and here are some islands, the Azoren Island, and the Azoren Island, they always have really good weather. Okay, it's maybe a bit rainy, but more or less they have good weather and sun. And now, why do they have so good weather? Or why is here good weather in Spain? Because you have a high pressure. Of course, there are more scientific explanation, but more or less you have a high pressure. And what happens if you have a high pressure? The high pressure pushes the clouds away, the sun can come through and you have good weather. But what will happen to the clouds? Well, what will happen to them, to the rain? You have here so-called isobaric lines. That's, maybe you can't read it, but you can refer to the slides and then you see it. Here are numbers, here I can read it for you, 1015, that's millibars, and here you have 1025 millibars, and here this is called an isobaric line, and everywhere on this line you have the same pressure. You have iso means equal or the same, yeah? Isobaric means there are the same bars, pressures. Okay. And this H means it's a high pressure region. Okay, now it's over London, that's not so often the case, but here more or less you have high pressure. But if we look at here, it's near St. Petersburg region, Finland or Iceland, you have a T and you have blue lines and you have really low pressures. Here in Iceland it's about 950 millibars, with a really low pressure. And what happens if you have such a condition, high pressure, low pressure, what is happening to the air? The air will flow from the high pressure region to the low pressure region and will take all the clouds with it. So we have a lot of rain in Finland and Iceland and here in this region. And on the other side, during their way over Spain and French, the air is taking a lot of clouds with it, and the air is pushing the clouds here also to the western part of Europe. And that's the main condition in western part of Europe. We have west winds and we get the rain from the Atlantic seaside. Okay, that's more or less the weather. If it's like this, it's okay. We can have other conditions. Sometimes we have high pressure over Russia, lower pressure here. This means really cold weather and cold winter time. We will have really narrow temperatures. Okay, so maybe notice pressure difference is the driver for the movement of a fluid. That's one of the main principles in computational fluid dynamics. High pressure, the fluid goes to low pressure and will have high velocities because of this fluid movement. On the other side, if you don't have a big pressure difference, you have a high pressure everywhere, you have low fluid velocities. More or less, you can explain it like this. Okay, here are the white arrows. Maybe you can't see them really good, but I've already explained it. So, let's look at our weather forecast and make it a bit more easy. We have our isobaric lines here, P1, P2, P3, and on these lines we have always constant pressures, isobaric pressures. And let's say P1 is the highest pressure, P2 is a little bit smaller, and P3 is the smallest pressure. So what will happen to a fluid if you have this isolines here? We will have a gradient in this direction that follows our arrow. And I've done this isobaric lines into a three-dimensional coordinate system. And so if you want to calculate this gradient, you have to make the derivation of a variable. Here it's called phi, or maybe we can take the pressure for phi and we can make the derivation of the pressure in every direction of this three-dimensional Cartesian coordinate system. Okay, so important variables are pressure, fluid velocity. You have to calculate the interaction between both. Let's explain it like this, and the solver will does it for you. But here in this chapter flow fields, I want to explain what we must visualize, and if we have an isothermal simulation, so no temperature movement, temperature is not so interesting at the beginning, we just look at pressure and we just look at velocity, and we have to visualize them. And both variables are difficult to visualize because both are not visible for us. We can't see pressure, we can't see velocity in real life. We have to invent some method to visualize them. Okay, and sometimes we have derivated variables, for example like forces. If a pressure is acting on a wall, we will get a force, or we will get a force, tension inside a solid. We will have, if we go more into details, we will also have turbulent flows. We have some really abstract variables, a turbulent kinetic energy, which is quite difficult and more advanced, even more advanced to visualize and to explain. So I explain it later. And of course here I will also only show you something about isothermal conditions with a constant temperature, so I won't show you flow fields, but if you make an adiabatic simulation or a non-isothermal simulation, it can be really interesting to visualize temperatures. For example, you make Cfd simulation of flames or heating systems or hot water systems or so. But that's now more advanced. We will come to this point, temperature, a bit later. Okay. I explained you a lot about velocities, and normally I like to show the students some experiments. I'm a bit of a freak in building something. I'm an engineer and I like to build experiments. And one experiment I really love is a classical elbow system. I explain it more often here. You can insert here some water into a channel, and into a smaller channel you can also fill in water. And I tried to build an experiment, and I had no really idea how to visualize the flow. Of course, one method is to take ink, yeah, or colorful water, and another idea of me was to take hot water and warm water, make the pictures with an infrared camera. And that's something I want to introduce it to you here, but I have much more and better movies on YouTube on my channel. Okay, these were some pictures. It's not so good to see. I also made some computational fluid dynamics simulations, but here is the experimental setup, and maybe the pictures are not really good. It was my first version of the setup. I didn't build it really good. Yeah, here you enter the water, and if you look on the slides, you can see here I had some ink. I injected some ink, and you can see the two different streams of the bigger water stream here and the smaller water stream with the ink. And what was not so bad, let's say not so bad, they don't mix so fast. You can see some turbulence roll, and you can see some streams of the blue water because it's a laminar region. It's not so, it doesn't mix so fast. Okay, here is a movie. I don't want to start the movie because it doesn't make sense to start a YouTube movie inside a YouTube movie, but you can you can search for this movie in my channel and start it on your own. Okay, that was the next step. I decided that injecting ink is a bit mess and the model was not so, not so really good. So I built a more advanced, and this is, and then I got this idea by visualizing of, I took different cold water and another temperature hot water, and then I injected the hot water, and then there I injected the cold water, and now it was possible to make some pictures with an infrared camera. They're pretty cheap now. Yeah, I bought a Flix camera for my iPad, and was easy to film it. And there I got some pretty nice movies and pretty nice pictures of the hot water stream, and you can even see some swirls and fluctuations in the water that are that must occur because of the Struhel number and the Reynolds number that we have in this condition. And what you see, we have time steps. Yeah, that's something that is important to visualize. Different steps. Here at the beginning, it starts at step 1, then comes step 2, step 3, step 4. Okay. And here's again a movie. I don't want to start it because for me it doesn't make sense to start a YouTube movie in a YouTube movie, but you can follow the link here. You have the slides in the Moodle system, you can follow the link, or if you want you can take your mobile or cell phone and film this QR code, and then you come to the YouTube movie. And I get some more colorful movies here. Okay, that's another picture I want to mention, and the quality is not so good. I took it from the source and an older picture, but here we have also a method for fluid motion to visualize flow fields, and here we have also a picture of translation, deformation and rotation, but also things that happen in fluid dynamics that can be showed. Okay, or here's a picture. I have some much better pictures like this. I made a lot of experiments with smoke. Here you see, these are not pictures from myself, but I have some pictures, smoke pictures, even better. You can follow them also on YouTube and QR code. And what you see here is an airflow over airfoil or NaCa profile, and you see the streamlines over the profile. And now if we change the angle of attack, and maybe when the plane lifts off, you see the change in the flow field by the changing streamlines. And this is smoke streamline. This is pretty hard to build up such experiments. We tried a lot to do it on our own, but it's difficult because you get condensation of the smoke really fast, and these great streamlines are fantastic. Normally you will have effects of condensation, and then you get turbulence, and then you can't see anything. Okay, here are also something I want to mention. I have a really interesting relationship to the Ars Métier in Paris. They have a great wind tunnel, and I visited them in 2018 and 2019, and they have a really old, really big wind tunnel. It's really fun to visit it. They have really good experiments, interesting experiments, and they have found some interesting models for cars. You see a Citroen car. And Citroën made a lot of experiments in this lab. And here's even an old DS model. And you can use them for experiments in the wind tunnel, for smoke experiments. So you have to build up the car. Today it's even much more easy. You can print it with with a 3D printer, then you can smoke experiments. Here another smoke experiments to visualize the fluid flow. That's a really big tunnel from Volkswagen, VW and Audi. You can see here this A2 Audi, and you see streamline over the car. They made these pictures in 2002. Or here is a Volkswagen Golf car, and you see really good visualization of smoke, streamlines, very laminar flow, and you see the turbulence behind the car. And then you can make optimization of spoilers or of the geometry of the car. Or this was another project where we wanted to visualize fluid flow, and we did it also experiments in the wind tunnel and of course CFD simulation. So we made streamlines for the visualization of flow around a truck geometry. And yeah, the aim was to examine some platooning problems. So we printed the trucks from the CFD simulation model and made the experiments in the tunnel. Okay, here's also something you might know. We have also good relationship to the Clemson Tigers. The students visit our lab, and they're great guys. And because I know you like the Clemson Tigers and you like football, I have chosen here such football ball. And of course I haven't done the simulation. It was done by Andrew Baker. I took from Fluent. He made this visualization, and here you can see the football is flowing, and what happens in front. You have here this violet blue region, and you have this yellow region, and this should show you the fluid flow around the football. And if you go more into detail, and for example if you want to visualize here this leather strips on the ball, you can zoom inside, you can visualize really good detailed regions, and you can show the lift off here by small arrows, and arrows are colored after the velocity. So that gives you the impression of a turbulence behind these leather strips. Okay. Or what is always good, yeah, here's again our friend for football. It's always good to make movies, animations. And if you have your CFD results, how can you make animations? Animations are really often an eye-catcher. If you have an animation of your CFD result, everyone will say, "Oh, fantastic! I understand the fluid flow. That looks pretty good." It was always during my work in the company. It was always an eye-catcher. And how can you do animations? It's a bit of work, but in CFD you do it by when you print different pictures, like in a cartoon. Yeah, you make from many positions or different values or different time steps a lot of pictures, and then you can produce from these pictures afterwards a cartoon-like small movie, MP4, and then you add it to your slide, or you even better as a GIF. If you generate a GIF from your picture bunch, you can directly insert it into PowerPoint, and you won't have any trouble with external links or integration into Microsoft PowerPoint. Yeah? GIF is always a good solution. It will be directly integrated in the PowerPoint, and you can share the PowerPoint and everything will work. Okay, that's something maybe we should learn during the lecture. Okay, here is another visualization method. We have again our laser strips, and now we have velocity plots. Yeah? You can visualize the velocities around the ball by the color of the arrows and by small arrows. Okay. Or here is the same, but you might notice visualization is not really so good. Yeah, you see a pattern. Maybe if you go to the slide, yeah, here is the position of the arrows is regular, and sometimes this is not such a good effect. It doesn't look so good as this picture, where you have irregular position of the arrows.